All right, welcome everybody. Welcome to the Path Seminar Series. It's good to have you all with us. For today's speaker, we're going to have Dr. Peggy Wang introduce today's speaker. So I'll hand it directly to you, Peggy.
Thank you, Scott. Hi, everyone. Can you hear me well? Okay, great. So it's my honor to introduce Dr. Xinwei Yang, today's speaker. Xinwei comes from a very beautiful city in the south part of China called Fuzhou. And Dr. Yang received his PhD from Intelligent Transportation System Research Center in the Wuhan University of Technology in 2024. And before that, he was a visiting researcher in the Mechanical Engineering Department in Eindhoven University of Technology in the Netherlands from 2022 to 2023. And Dr. Yang's research interests are about the vehicle lateral and longitudinal dynamics and cooperative adaptive control for vehicle platooning and nonlinear and adaptive control design. As you can tell, it's not much related with my research focus, but interestingly, Dr. Yang is going to work with me in the next 1 or 2 years on 2 Caltrans projects. So one is about automated vehicle data sharing. The other one is about work zone data exchange. So with that, Xinwei, the floor is yours.
Hey. Hello. Oh, okay. It's really appreciate Scott invite me to share this presentation and introduce my PhD work for the Path team, and the ITS teammates. Yeah, it's a great honor. So let's start.
Yeah.
Okay, I share the screen.
Please.
Okay. Then here I will sit here or stand.
Whatever works for you. Whatever you're comfortable
It's okay.
You're in charge. You're the boss.
Sit here is okay.
Yes, that's okay.
Wait. Hi everyone. Today I will introduce the work in my PhD thesis. It's about heterogeneous cooperative adaptive cruise control from linear system to nonlinear system. The agenda of my presentation has 4 parts. Firstly, I will do an introduction for the CCC system. Next, I will show the linear system and from linear system to nonlinear system. Finally, is the selected references. Firstly, I will introduce the background of cooperative adaptive cruise control. This control system, firstly proposed actually is a UC Berkeley Path Institute. I can see from last century, a lot of researchers have focused on this problem. It can be seen as an extension of adaptive cruise control. Adaptive cruise control is very common in today. Most cars are equipped this system, but some researchers see can we use the V2V vehicle awareness communication method to improve the control performance of ACC system. Some experiments and the simulation has shown result is right. If we use the V2V communication, the follower vehicle can receive the preceding vehicle states. Then they can maintain a safe and shorter inter-vehicle space. The objective is to improve the string stability property. It's a very core property for vehicle tuning. Finally, if they use, they can achieve, they can enhance the low threat and improve the fuel efficiency using the cooperative adaptive control system. Next is the next I will introduce some vehicle tuning models. First, actually, the vehicle longitudinal dynamics is a nonlinear model for the actual vehicle. We can see in this part, it's a three order dynamics related to position, velocity, and force. Finally, we can get the right part. The right part is when if we substitute the V dot into this part. This formation is we want get. It's about position, velocity, and acceleration, but it's still a nonlinear dynamics. If we know the vehicle actual dynamic parameters like vehicle mass and some lorry resistance, we can use the feedback linearization to get linear dynamics. We can most research they hope to simplify this problem to a linear system. Whatever you use nonlinear or linear system, our objective is to objective is to control to design how to design a controller to make a system stable. Vehicle platoon. Next, I will introduce another topic is about heterogeneous dynamics. We can see the left, all the vehicle are the same. They use Toyota vehicle like Toyota vehicles. All the vehicle is the same. It can compose as a homogeneous platoon. But in the left, right part, we can see some truck, some passenger car. They compose as a platoon. We call, but all these vehicles have different vehicle dynamics. We call this type as heterogeneous platoon. Yeah. For the linear system, we most focus on driveline time constant difference. But for the linear system, we can see vehicle mass and aerodynamics and lorry resistance and external winds. Some parameters is different for each vehicle. Next, I will begin my introduction for linear system. Start from linear controller design for linear system, especially for the heterogeneous system. We can see here, I do a compare for two works. Yeah, for linear system, we'll assume all vehicle parameters are known for each vehicle. So we can use the feedback linearization to simplify the vehicle dynamics. And then, firstly, the proof propose free order aerodynamics. Yeah, here. Yeah, and he proposed vehicle control, and but this controller he used the preceding vehicle like here CU I-1 is the preceding vehicle comment controller. It will transmit to the following vehicle. But on the right, yeah. Area propose another controller to is shown this, but the difference is one is use the vehicle actual, the preceding vehicle actual acceleration. Here is use the controller command. We can see here this problem for heterogeneity dynamics system vehicle platoon. It required preceding vehicle driveline dynamics and the individual dynamic. But here you use this personal vehicle dynamics tau I is okay. Yeah. So we call this ACCC framework as ACCC. ACCC is more suitable for linear heterogeneous vehicle platoon than use ACC.
Xinwei?
Yeah.
The aerodynamics epsilon is the error between what two quantities?
Quantities. What you mean here?
What is the error?
Area. Yeah. Quantity.
What is the definition of the error? Epsilon?
Yeah, different is here he used the
Epsilon 1 is position error.
yeah. Epsilon
error
1 is
between-
position. Yeah, epsilon 2 is the velocity.
But error between what things?
Area use two orders. Actually, he used two orders. Differential equation. But proof use a three order differential equation to do this work. So this is proof controller design.
No, my question is,
Yeah.
okay, epsilon 1 in aerodynamics 1. Let's just focus on epsilon 1 in aerodynamics 1.
Yeah.
It's a position error
Position. Yeah.
between the ego vehicle position, or sorry, it's an error between vehicle I
Yeah.
and
I-1 and I. The dynamics is the safety distance, and the actual distance minus safety distance is the epsilon distance.
I see. So it's the error with respect to a desired set point.
Yeah, set point.
So the desired set point for position would be a safe following distance.
Yeah.
The desired set point for speed would be a desired speed,
Yeah,
non-zero speed.
they use the headway.
Mhm.
How to say?
Yeah, headway.
Headway, yeah, following process. Headway.
Yeah.
Yeah. The difference is here. Area he used the acceleration,
Yeah.
actual acceleration.
Yeah.
But proof he used the controller comments. Yeah, that's the difference between this model.
Okay, I'm good to continue.
Yeah, we can talk after this meeting. Is okay.
Yes.
Continue. Yeah. 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 Next one is I find AC system with driveline delayed has a driveline delayed when I do some simulation or experiment. Yeah, it's a problem I have to solve. So for this problem, yeah, we can see here. If the system is non-driveline delayed, we can find we can get a perfect checking and performance control performance. Yeah, the acceleration and the distance arrow, yeah, it can approach it to 0. Yeah, it's perfect. But if the system has the 0.1 delayed, a driveline delayed, yeah, we can find the control performance was degraded if we don't do any compensation or someone. Yeah, yeah, here next I design a controller with compensation. Yeah, this 5i. 5i is the system driveline delayed. I will identify this delayed before my experiment. Yeah, you can see here. It's sorry. We can see here. Yeah, we can get in the same input and the same driveline delay. We can get a good acceleration checking and good the system distance arrow is approaching to 0. Yeah.
This delay is constant.
Actually, it's constant. Maybe it depends on vehicle speed. But for the experiment, we can see it as constant. Yeah, for experiment, we can see it as constant. It's no problem. Yeah, just do a composition.
Yeah.
We can set it has a view. We do a parameter identification.
Yeah.
Yeah, before our experiment. Yeah, we can find. Yeah, next is this system. It has a core property. We call it string stability. Yeah. Yeah, the proof also define the string stability. Yeah, in 2020, in 2030. Yeah, 2030. Yeah, it present. He said we not only should define should satisfy the steady state stability, but also we should guarantee the system the norm of current vehicle state norm is not exist the preceding vehicle. Yeah, so their norm the norm is the value is less than 1. Yeah, we can say this system is stability in frequency domain. We can see here. Yeah, they are present. Yeah, if the read line it exists 1, so the system is not stability, but others is stability. Yeah, it's good. Okay, the headway is considered as the function of driveline delay. I hope in the same condition, if we can use the smaller headway, yeah, to control the vehicle platoon, which means the protein has a better sensibility ability. Yeah. If we use the critical sensitivity condition, yeah, we let it's equal to 1. Yeah, use the bisection method. Yeah, to see what will happen for communication delay and the drive line delay. Yeah, we can use the headway as the function of these two states, these two time delays. Okay, fine. Use our work improve method. We can, if the system is no compensation for any delay, it should use the maximum in the same delay. It require larger minimal headway to maintain the vehicle in sensibility, yeah, state. The Smith predictor has also the same performance compared with my proposed method. Another says okay. Actually, in the real experiment, we also there exists some sensors noise, yeah, for our experiment. So I have to design a observer to eliminate the noise disturbance. You can see here is the simulation. Yeah, here is the value of some variance for the measurement sensors. You can see here if we don't do any filter from our system, the distance errors will be larger and larger, and then the system is without noise. Yeah.
So in this case, you can still measure all the states. You're just using the observer to filter noise. Is that correct? It's not an issue of being able or of not being able to measure speed, velocity, or force. You can still measure those things. You're just using it as a filter. Is this correct?
The filter I use to observe the acceleration. We can use accelerometer to measure a vehicle acceleration. Yeah, it's right. And the distance and the velocity error, relative distance and the velocity, we can use radar to detect the distance. But there also exists some noise. Yeah, we get. So we have to filter the noise. Yeah. So it should combine with the observer. Yeah, controller should combine with observer. Yeah. So I design the acceleration observer and the distance and velocity error observer. Yeah. Yeah, it's the framework can be seen as an extension for the driveline delay. Yeah. I call it observer-based ACC system. When I use the observer, you can see here the simulation result. Yeah, here. Yeah, especially focus on the distance error. Yeah, here. It's very approaching to 0. Yeah, it's good.
Can you remind us again, what is the amount of, so I see that the driveline delay is something like 0.15 seconds. 0.15 seconds?
Yeah, 0.5 seconds. Yeah.
The communication delay, how much is that?
Communication delay.
Maybe it's your last slide.
I don't that communication delay. It's 0. It's zero.
in this slide. Can you go one slide back?
Back, okay.
Yeah.
Yeah, it's the driveline delay. Yeah, I don't
No, there's the one where you were using bisection method to calculate the minimum headway to
Yeah.
ensure stability. And you had a three,
here.
communication delay. So,
Yeah,
so here you look at
we can
up to
see
1 second.
1 second. Oh yeah, here
I'm trying to
it's a
understand.
range. It's a range.
Right,
I don't
right.
care what the communication delay what's its value. It's a range. We can see here. I don't
Yeah.
do the compensation for communication delay. Maybe it's my future work. Yeah, communication delay. I
Okay.
only do the compensation for the driveline delay. Yeah,
Okay.
controller is focused on here. We can see here is a range. It's okay.
Yeah, I'm trying to connect with other people in the audience with your talk of just getting, so this is, the communication delay is like vehicle to vehicle communication,
Yeah.
right? And then do you have an idea of like in real life, what might be typical range of vehicle to vehicle communication delay?
Yeah. Area he do yeah. I have actually they use the robust control theory for the proof Professor Proof use the robust to consider the worst case
Yes,
to make it to compensate the communication delay. Yeah, but communication delay in actual texting it's hard to measure. It's hard to measure. It's a variable. It's a variable.
right.
Yeah. So
Okay, and another quick question before you finish. Your compatriot, Demetrius Kapsalis, your postdoc compatriot, he's asking about the driveline delay. Physically, what causes the driveline delay?
driveline delay, yeah, it can be seen as the
Actuator delay.
actuator delay. Yeah,
Okay, physically, what causes actuator delay?
Physically causes.
Yeah,
Yeah. When I do the testing, I found if I input a single to the vehicle, yeah, it has the output single has is different with what we input. Yeah, has a the input single will sorry we can measure a single. Measure a single is different with our input. Like we input
yeah.
input plus single how to say
A pulse signal.
pulse single, yeah, pulse
Yeah.
single, yeah. It cannot perfect check it. If we use the measured data, yeah, measured data.
Yeah.
So there has here has some delay. We can see here. So we
But what causes that delay?
delay.
Yeah, you observe it. Now explain it.
Okay, we call it
Actuator delay.
actuator delay. Yeah, it's the machine like we input. It has some delay. Yeah.
Yeah, right.
Go
right,
through.
Okay, that's fine. We'll continue.
Actor is EUTORT. I don't know spell this delay. Maybe I can send you a message after this meeting. Yeah.
Yes.
I know what it means, but I don't know how to explain now.
Yeah, send it
Yeah.
to Demetrius. He's asking this question.
Okay. Yeah.
We keep going.
Yeah, keep going. Yeah, it's up to observer design. So I have to see if we design the observer, there's some observer gains. The gains how we choose turn, how to setting, or we can call it turning the observer gains. And I try to find its relation between stability. Yeah, okay, we can get the linear system. We can easily get the transfer function. It's very easy. Yeah, it's okay. And then we design the observer. My objective is to find can we set the observer gains and make the system it has the better control performance approaching to the ideal CSC system. Yeah, we find here is common delayed and the driveline delayed. If I selected different controller observer gains, yeah, it's more and more approach. Oh yeah, the read dash is our ideal CSS minimal headway performance. Yeah, we hope it can approach into here. So I selected the value larger and larger. It's more and more approaching to the ideal CSS condition. Yeah. Next is about the CSS and the communication interruption condition. Yeah, we will find it if the well-code platoon going to a tuning or some bad condition environment. The problem is to how to design a controller for the degrade CSS system. Some the papers has shown that if the CC system with 150 millisecond delays, it should state 0.7 headway to maintain the vehicle traceability. But if the system, the communication is broken, if the system wants to maintain the same traceability, it require increase the headway to 3.5 seconds. Yeah, almost yeah, it's so it will increase the vehicle following distance. Yeah, no problem. So so my work is to try to design a controller to make the system not directly degrade to AC system when the communication interrupted. Yeah. So the controller design use the previous controller. Yeah, here is the problem. We cannot, if the communication broken, get fault, we cannot receive the preceding vehicle acceleration again. Yeah, here you can see here AI -1. So here I use the hat, and we can see it as an estimate state. Here, if -1 if the vehicle is broken, we use the ACC system. Here it can be seen as a 0, but actually it has a value. If we can estimate this value, it's perfect for us. So I design a linear heterogeneous CCC based on the state observed and delay computation. It's my previous work. Yeah, and here I use the previous framework. I use the single acceleration model. and combined with the if they use the S domain to a time domain is transfer. Yeah, we can get the expression of preceding acceleration acceleration expression is related to relative distance and the relative velocity and some acceleration, the vertical acceleration is perfect for us to draw this framework. Yeah, here. Yeah, if it can be estimated, I can do some simulation here. You can see here the CC system, yeah, is our ideal system. Yeah, it can achieve a better expression in the time. We say the time headway is 0.5 seconds. Yeah, but if we use the DACC system, yeah, it's a degree CC system, but with the estimate the acceleration observed, we can this distance L is between minus 1.5 to 1 meters. If you use the AC system, its distance L will increase to at least 5 meters. Yeah, and we can calculate their each vehicle its norm. You can see here AC system it can its norm is always get decreased. But the ACC system, its norm is a little bit increase. ACC system increase significantly.
Xinwei, just zooming out for a second, it seems you're generally trying to minimize headway, right?
Yeah, I can.
Can you say why?
Yeah,
Like, why is that a goal?
Yeah, the headway can be seen as the index for the string stability. If we call like in the same condition, use the a smaller headway. Yeah, the vehicle can follow each other in a short distance. We can improve the throughout the traffic throughout efficiency. Yeah, and some yeah from the point of aerodynamics, it can improve the fuel efficiency.
Okay, improve throughput and potentially improve fuel efficiency.
Yeah. Yeah.
Okay. Thanks.
But if we increase the headway to 2 seconds, we can see here the best state is also the CAC system. The performance of a degree CAC system has also some improved. You can see here from its distance arrows. But the ACC system still required its tracking performance still reduced and didn't get some improved. Okay, next is a frequency domain. The previous is from a time domain. Next is frequency domain. Yeah, we can see here. If the system has the ACC system has 50 and 80 seconds delay, a communication delay. You can see here the blue and the red. When the communication delay increased to 80, yeah, its norm value will exceed 1, which means the ACC system lose its stability. That from here you see DAC system and ACC, they are not related to a communication delay. It's their value, DACC and ACC. Yeah, ACC has the voiced frequency performance. Yeah, here, whatever it's used, which time headway. Okay, next is the minimal headway. Yeah, we can find here. It has a relation between the ACC system has a relation between local communication delay. ACC system, it will increase with the time delay. But these two, they have a constant value. We use the bisection method to calculate it. Yeah, it's the DAC system. If it can keep 1.7, yeah, it's perfect. It can, if we select it, if the time headway is not larger than 1.77, we can guarantee the DAC system is a sensibility. But if we find here the AC system, it have to reach 3.5 time headway to keep the system sensibility. Yeah. Okay, next is the simulation result. Compare with the proof work. We use the same. We compare with the proof work, and we try to turn the observer parameters. Yeah, I can get some result here from here. It's the DACC system is my proposed methods. The DUC system is the proof work. Yeah, okay, fine. Here they have some overlap, but when some parameters increased, the control performance will lost for the previous work. Next is my design experiment to verify my controller. Yeah, here's two wheel code, tiny wheel code, we call it tiny wheel code, and the controller will calculate it by my computer. And both wheel code, they can communicate from Wi-Fi. Yeah, they are all in the same load node.
They communicate between each other.
Yeah.
With Wi-Fi.
From Wi-Fi, sure. And both vehicle they equipped IMU to measure their states.
Mm-hmm.
Yeah, it's there. Here is their yeah, it's some demonstration. I've tested 2 vehicles and 3 vehicles. Yeah. Yeah, it's the simulation. It's an experiment in real world. Yeah, it's the experiment result. Yeah, it's actually has it's we can see here ACC and our proposed DCCC and ACC system. Yeah, ACC it can achieve best control performance and adapt it because it has always received feed forward signals from preceding vehicle. Its acceleration and yeah, in different time headway. Yeah, I tested it. And next is the distance arrow. Yeah, distance arrow. We can see here CC system in good communication case, it can guarantee the distance L approaching to zero, and the velocity L is also approaching to zero. But the AC system has the voice control performance. Here you can see here it's a larger. The second choice is this DACC system, the degree ACC system with an acceleration estimate. Next is our work for three cars. Yeah, I tested with observer and the non-observer. Yeah. Here is the non-observer. Is the observer. Is observer. And the vehicle with different loads. Yeah, also tested. Yeah, it's our experiment result. It's okay. Okay, next I will introduce about nonlinear system. Nonlinear system. The problem is in actual vehicle dynamics, we cannot exactly know the vehicle parameters like its mass. Its mass will change with the loads and the cargo and some passengers. Weight. Yeah, it will always change. With this change, its loading resistance and is also change. The wind, the aerodynamics is also changed. But this change is not a sharply or variable. This parameter can be seen as a constant in some case. In my work, I do an assumption. Yeah, assumption for this.
So it's constant but unknown.
Yeah, it's constant but unknown. No change.
By the way, we have about 3 minutes. Do you think
Oh
you
yeah,
you can finish?
Yeah,
and-
finish. Okay. Next is the here I start from nonlinear dynamics. Yeah, it's position, velocity, and acceleration. Yeah, here. So my object is how to design UI to make this system achieve Lyapunov stability. Here I define the aerodynamics. Yeah, here is the three order aerodynamics. Here, so I have idea for how to design the controller for this system with unknown parameters. Mostly, we can use the adaptive control. Yeah, it's a very common method for us to do this work. But adaptive control has the traditional way has some limitation. Especially it requires a strict persistency excitation condition to make this system get into a robust. So I design this is the best line here. We can see here the orange line is the best line if we use the traditional way. Next, I design here is my improved is here. I add another items. I call it theta head dot 2. It's all I designed. More detail maybe it has been published in my work. Afterward is to my idea is to how to guarantee the unknown parameters converge to the real value without require the persistency excitation restriction limitation.
Xinwei, we're at the 1 hour mark. So can you go to the last slide and just
Okay.
conclude?
Yeah.
Last slide, please.
Oh yeah. Yeah. Here is here is my stability analysis. Yeah. The stability and the robustity is my framework here. It's a algorithm to in my work to make the controller always update their eigenvalues. And its eigenvalue, yeah, it has more and more details. I cannot say more details. Yeah, here maybe you can talk in our next in our meeting after meeting. Yeah, it's oh I missed some simulation results. I don't know where it is. Sorry. Yeah, I don't know. Oh,
That's okay, Xinwei, because if
Okay,
you had
okay.
them, there's not time to talk about them.
yeah. Okay.
So maybe we can.
Yeah.
Great, let's give him a hand, thank you.
So I want to first off applaud your consideration of data limitations, namely when during communication failures and not knowing the mass and force of other vehicles. But what I'm concerned about is related to this, which is the effect of the order of vehicles. Different vehicle types. What happens if you have the vehicle at the head of the platoon
Yeah.
that is a very slow accelerator that won't accelerate fastly?
Yeah.
Or you have a vehicle that has faulty braking. So some of these things you could get data for necessarily, and others you may not be able to. So I don't necessarily have a question related to this, but that is what stood out to me throughout is the effect of the order of different types of vehicles, because you were talking about a heterogeneous platoon.
Yeah.
Where you have semis and you have passenger vehicles, and those vehicles have different performance characteristics. So it's something that I think when considering the platoon as an entire system would be relevant.
Yeah, it's very relevant. Yeah. I mean, yeah, different vehicle they compose with composed as a vehicle platoon is very common in actual traffic case. Traffic case is it's no problem. It can be randomly composed in the ideal case. Ideal case if they have the vehicle to vehicle communication. So can you repeat your question?
Well, I didn't necessarily have a question. It was just more of a point that when considering a cooperative ACC system,
Yeah.
one of the factors that would influence the decisions being made by the adaptive cruise control system is actually the order of the vehicles themselves.
Yeah.
Because the way I understand it would be a vehicle near the front of the platoon is going to have more of an influence over the entire system than a vehicle elsewhere in the platoon. And so how does the actual order of vehicles within the platoon affect your optimization? It's not so much a question that needs to be answered now.
Yeah, it's not. I don't consider the vehicle platoon order is problem. Yeah, I just consider how to make them cooperative. Yeah, their states we can check each the preceding states.
Let me frame it this way. I think the question is, there's two problems you mentioned. One is delay, driveline delay communication.
Yeah.
The other one is heterogeneous fleet. Imagine giant truck, small vehicle.
Yeah.
So you study control laws that maintain robust stability in the face of delay. And I think Michael's question about order is really about control laws that ensure robust stability in the face of extreme heterogeneity. Tiny car following big truck, or big truck following tiny car, because their dynamics will be different. Sounds like an interesting problem.
Yeah, dynamics. I consider this problem. Yeah. I don't care their dynamics, local dynamics. Yeah. I can estimate. I try to eliminate it, the parameters uncertainty. So the controller is distribute
I
for
see.
each block. Yeah.
Okay, so you have to estimate the parameters in the order that they're
Yeah.
the platoon order. Yeah, okay. James, you had something?
Yeah, but if we're out,
Right.
I can just so we've been working on platooning here at Path for going on 30 years now, right?
Yeah.
And I guess this is not specific to your research, but more broad. What do you think it will take for us to see platooning in the real world? And what would it look like?
Yeah, it's not easy for the platoon go to the real world.
Yeah.
Yeah, not easy. Yeah, to be honest. But in my work, I just to try to see the communicate can use the vocal communication to improve the vocal control performance, especially for this multi-agents. And try to design different different controllers for this. But if we want to put it forward to real world, it still has a lot work for me to do from sensor and some
Maybe this will be my last point. Maybe I'll be more specific. Based on your work, and you spent a lot of time doing this, are there specific use cases that you think will be more attractive for deployment in or outside of the US? So like, for example, would you think that drayage routes for trucks make the most sense on a dedicated lane?
Yeah, most case for the trucks, because trucks they can compose as a platoon to deliver the cargo or something. Yeah, the logistics industry maybe can require it. The first vehicle truck it said we assigned a driver, but the following vehicle we don't require the driver. Yeah. Some labor. Yeah. Cost. Yeah. And for the large truck, if they can drive in a cooperative behavior, the fuel and consumption can also be decreased. Yeah, I guess. Maybe
You already see truckers do this. They draft off each other, where truckers will team up and you'll have one semi-truck following the preceding semi-truck very closely.
Yeah.
And an outsider viewer would say, oh, that's actually too close. But what they're doing is the latter trucks are getting the aerodynamic benefit from the truck being in front of it.
Yeah, sure.
So, yeah.
It's a nice benefit. But the actual scenario traffic for traffic condition is really complex. If in the no human or a relative safety testing testing scenario, it can be realized. But in real cases, it still has a lot of work.
Yeah. Okay, we need to close up.
Okay.
Thank you.
Thank you, Xinwei.
Yeah.
Amazing.